Today we are going to be talking about finite system notation. I want you to notice here that this is a finite system notation like this. This is how we would notate and talk about Johnny's clock arithmetic. So notice a couple things. First of all, we call these Z systems because here's a big letter Z. And then notice that the number of elements I have is this little subset. So if I had a system with 5 elements, I would write that as Z5. And then notice that I have a comma, and then the next part within my parentheses is my operation. So if I were in a system of Z5 addition, I would put an addition sign. If I were in a system of Z5 division, I would put a division sign there. So that's our finite system notation, and we are going to look at some numeric finite systems where they have numbers, and we're going to look at some non-numeric systems like this. So if you see here, this is a non-numeric system, and you can see the headers. The elements in this system are L, U, and V. The operation is a heart. So if I was talking about what is L operated or hearted with V, I would look and go to L first, and I'd go across to V, and I see that equals L. So if I tried to look at V operated with L, I would go to V, and I would operate with L, and I would also get L. Cool. I wonder what U operated with U would give me. Let's see, U operated with U, that would give me V. Now, before we move on talking about more numeric systems, notice when we looked at Johnny's clock arithmetic, the row and column of 12 should have stood out to you. And hopefully you noticed that anything plus 12, or 12 plus anything, just gave you what you started with. And so 12 behaved like what kind of number? What number that we are familiar with? A whole number. All right, so 12 really behaved like a 0. So actually, instead of 12, we are going to refer to this as 0 from now on. So this is a change. We used to think of Johnny's clock as having the elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now I want you to change your approach and think of it as having 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So in other words, when I write Z12 addition, that is going to have 12 elements in it, and those elements are going to be 0, 1, 2, and so on, all the way up to 11. Make sure this is 1 less than this number. So now that we're getting used to this notation, let's have a look here. So I'm going to ask you to give the number of elements over on the right side, and also I'd like you to list them. So Z9 multiplication, my operation is multiplication. How many elements? I have 9, and to list those I would start at 0, 1, 2, 3, and I'd go all the way up to 8. If I had Z23, think about what operation, how many elements. My operation is division. I'm going to have 23 elements. I'm going to start at 0, and I'm going to go up to 22. Z3 addition, my operation is addition. 3 elements, 0, 1, and 2. So make a note that when you look at this number, that is the total number of elements, but you don't ever actually have that number in your system. So notice Z3 does not have 3 in the system, because 3 is the same thing as 0. Now, this would mean whole number addition. How many elements? Well, I have an infinite number of elements. It would be 0, 1, 2, and so on. So, what system am I showing you here? Please just ignore the yellow parts. So this is some sort of Z system. How are you going to find the operation? I'm going to look right here. So my operation is multiplication. And how many elements do I have? I have 1, 2, 3, 4, 5. I have 5 elements. So that means this is called Z5 multiplication. That's what this system is. Let's look at this one. And we have so much writing on here. I have an idea. Wait, no, stop. Okay. Ah! Not that. Oh, really? Oh, whoa, mute. Okay. Let's erase. And size this down. Okay, now let's look at this. Okay, now we're looking at this system. What system is this? Well, it's a Z system because it has numbers. My operation is addition. And how many elements do I have? I have 5 elements. And yeah, it makes up that it only goes up to 4, because this number is the number of elements, but it doesn't actually, it's not ever in the system. Because I start at 0 and I go up to 4. So let's talk about how do we do computation in a Z5 addition system. We used a clock with Johnny. We can use a clock again. So if I'm given 3 plus 1, I get 4. 2 plus 1 is 3. I'm cool, I'm groovy. The thing is, when I do 3 plus 4, I get 7, but I know I'm not allowed to have 7. So how would Johnny do it? He would start at 3, and then he would go 1, 2, 3, 4. Okay, so this should actually be a 2. Now if I do 4 plus 2, I know it's supposed to be a 6, but I know that's not in my Z5 system. 6 doesn't exist. So how do I get back in the system, so to speak? So I'd start at 4, and I'd go 1, 2. Oh, I'd end up at 1. So 6 is really equal to 1. Now 3 plus 3 is also 6, but still I'm not allowed, so I'll start at 3. I go 1, 2, 3, and I end up at 1. Cool. Now 4 plus 1 really gives me a 5. Cool. Wait. I'm not allowed to have 5 because this is Z5. It only goes up to 4. So it can't be 5. So let's go to 4 and we'll count up 1. 1. Oh, okay. So 5 is really 0. So hopefully we're going to get away from using this clock. You could, because someday we're going to have a system that's like Z23 or Z98. That would be an annoying clock to make. So we've got to figure out a trick. How are we supposed to just automatically know this is 2? Without going dink, 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 and counting around. So there must be some relationship between the 7 and the 2. The 6 and the 1. The 6 and the 1. The 5 and the 0. It might have something to do with this.